Professor Harry Porter of Portland State University. Recently, I built a computer out of relays, and you can see it behind me. In this video, I'm going to describe how it works and explain my design in quite a bit of detail. So let's get started. The first question to ask is, what exactly is a relay? At the center of every relay is a coil of wire. When you pass an electric current through a coil of wire, a magnetic field is created and it becomes an electromagnet. Located next to the electromagnet is a small switch which will be operated by this magnetic field. This switch is held in one position by a small spring. When current is applied to the coil and the relay switches on, the magnetic field will move the switch into a different position. When the relay is off and the field collapses, the switch will return to the original position. All the relays in this computer contain double-throw switches, which are also called on-on switches. When the relay is on, electricity can pass through the double-throw switch along one pathway. And when the relay is switched off, electricity can still pass through the switch, but it follows a different route. All the relays in this computer are 4-pole relays, which means that they contain not one, but 4 switches. All 4 switches operate together, opening and closing in unison. When the relay is on, all 4 switches are in this position, and when the relay is off, all 4 switches are in this position. This is a picture of the actual part I used in my computer. For simplicity, I used the same part throughout the computer, although not all contacts or switches are used in every relay. You can see the contacts down below, and you can see a plastic cover which encloses the coil and all 4 switches. By the way, the first computer bug was a moth that became trapped between the contacts in one of the switches in an early computer. It got electrocuted and its carcass remained in place, preventing the switch from operating properly. I should note that since my computer uses relays that all have this plastic case, I have built a computer that is, of course, immune to all such computer bugs. There are several ways to represent relays schematically. On the far left, you see the traditional schematic diagram for a relay. In the center is a representation in which the positions of the contacts accurately match the physical relay part I used. This sort of diagram is particularly handy in wiring diagrams. The diagram on the far right is something that I came up with. Its simplicity makes it ideal for use in complex circuit diagrams. I show only one connection for the coil because in this computer each relay always has one coil connection tied to ground. The connection to ground is implicit in all my diagrams. Normally the relay is shown in the off position like this, but sometimes I'll show the relay in the on state like this. Next, let's use a relay to implement logical negation. On the right, you see a single relay implementing the logical NOT function. When the input is low, the relay is off and the output is connected to power. Our convention is that logical 1 is represented as a connection to power. However, logical 0 is not represented as a connection to ground. Instead, logical 0 is represented by a wire that is simply not connected to power. Tying it to ground is unnecessary and, in the case of a design mistake, could easily result in a short circuit. When the input changes to a 1, the relay switches on, and the output is then disconnected from power. Next, let's look at an implementation of the logical OR function. If either input is a 1, then the output should be a 1. On the right, we see an implementation using 2 relays. Each input will power one of the relays. If either relay is turned on, then the output will be tied to power, and the output will go to a logical 1, as it should. Now, you might suggest that a much simpler circuit would work just as well. On the right, we've implemented the same circuit with 0 relays. This is called a wired OR. If either input is tied to power, then the output will be tied to power. The wired OR circuit will work in many cases, but you have to be careful. It won't always work. Consider what happens if you try to implement the circuit shown on the left using the wired OR technique. Consider the case when D is high and the other two inputs are low. The C or D output should be high, but the B or C output should be low. Unfortunately, electricity has the nasty property of being able to travel down a wire in both directions. What's happening here is that the D input is traveling back out through the C input. In other words, a signal is traveling through the wire in the wrong direction. I call this problem backflow. Here's a version of the same circuit using just one relay to avoid this backflow problem. Sometimes you can get away with a solution using wired OR, and this can save a relay or two. But you've got to be careful that backflow doesn't cause some other circuit to malfunction. Next, let's design a circuit to implement the common logical functions of NOT, AND, OR, and exclusive OR as a function of two inputs, which we'll call B and C. The inputs are on the left and the outputs will come out the right side. To avoid backflow out of this circuit, we'll only use the inputs to drive relays. The circuit is kind of complex, so let's start with just logical negation. Here is the NOT circuit that we looked at earlier. Notice that logical NOT is just a function of the B input. C is ignored. Next, let's add in the logical AND. Both relays must be on in order for the output to be connected to power. Let's show what we've got so far in gray to keep things simple. Now we can add in the circuit for logical OR. And finally, we can show the circuit for the exclusive OR function. The output will be low if both inputs are low and both relays are off, as shown. If either input then switches on, then the output will go high, but if both switch on, then the output will again be low. Here's the completed circuit. We'll call this the 1-bit logic circuit. We can combine 8 of these circuits to create an 8-bit logic circuit. There are still 2 inputs, but now each input is an 8-bit quantity instead of just a single bit. The output is also an 8-bit quantity. Next, let's look at the circuitry for performing addition. Do you remember the definition of the full adder circuit? It operates on 1 bit in a multi-bit addition. It takes 2 inputs, which we'll again call B and C, as well as a carry input from the previous stage in the addition. It produces 2 outputs. One is the sum. This is the output for this bit in the addition. The other output is the carry output, which is fed into the carry input for the next stage. On the left is the truth table for the full adder, and on the right is a simplified diagram for the circuit. I'm not going to show the details of this circuit, but it is similar to the 1-bit logic circuit we just looked at. In the 1940s, Konrad Zuse in Germany came up with a clever design for a full adder using only 2 relays. His circuit for the full adder is the only circuit in my computer that I did not design myself. So now let's take 8 of these full adder circuits and combine them to form an 8-bit adder. Again, we have 2 inputs called B and C. Each input is 8 bits, and the output is 8 bits. A subscript of 0 is used for the least significant bit. Notice that we are feeding in a 0 as a carry in to the full adder at the least significant end of the adder. On the other end, the circuit produces a carry out from the entire addition. This carry out at the upper end could be used, for example, in testing for overflow or for performing larger additions. For example, a program for this computer could use the 8-bit add instruction repeatedly to achieve the result of a 64-bit addition. We can summarize the entire 8-bit adder circuit using the traditional circuit diagram for an adder, shown below. Up to now, each line represented a single wire. Here, the heavy lines with the little diagonal marks labeled 8 stand for 8 parallel wires. This technique of showing multiple parallel lines will simplify our drawings in the future. From time to time, it's useful to know when a value is 0. This circuit can detect when a value is 0, namely when none of the lines is high. Along the bottom, we see 8 wires, called the result bus. This circuit detects when a result, such as the result of an addition, is all zeros. The output is labeled 0 and will only be high when all the relays are off. We'll also be interested in whether an 8-bit result is negative or not. Recall that when representing integers in binary, the most significant bit is called the sign bit. We don't need any relays to compute the sign bit of a number. We could just peel off the most significant bit and label it the sign output. If the sign bit is 1, the value is negative. If it's 0, then the value is positive, or possibly 0. The next circuit to look at is called the enable circuit. It contains 2 relays, and both are driven by a control line, which is labeled enable. When the enable input is high, the relays turn on, and the circuit allows an 8-bit value to flow through, say from top to bottom. For example, the enable circuit might be used to allow an 8-bit value to flow onto a bus. Or it could be used to allow the value to flow from the bus to the other circuit. When the enable circuit is off, as shown here, the bus is isolated from whatever circuit is connected. For example, we can use an enable circuit to connect the exclusive OR output from the 8-bit logic circuit, which we talked about earlier, to a bus, which we will now call the result bus. If we want, as our result, the exclusive OR function, we can drive the enable line high, and the exclusive OR output will then be connected to the bus. This diagram also shows 8 lights connected to the exclusive OR lines. These lights monitor the exclusive OR output, regardless of whether it is connected to the bus or not. The exclusive OR is being computed continuously and is being displayed continuously, regardless of whether the value is being used or not. I've used the traditional circuit notation for a lamp here rather than for a light-emitting diode, although the computer actually uses LEDs. The actual part that I used is meant to be used as an indicator lamp, and it consists of both a diode and a small resistor, which are combined into a small plastic unit. All the LEDs are wired in the same way. One terminal is connected to a wire whose current value we're interested in seeing, and the other terminal is connected to ground. Obviously, the LEDs do not affect the computation. They merely allow us to see it and observe what's going on. But these LEDs are critical. Every computer contains a lot of internal state, and without them, it would be impossible to know what's going on inside the computer. We've talked about addition and the logical operations of AND, OR, NOT, and exclusive OR. While we're at it, let's also show how we compute the shift function. It's really easy. We don't need any relays except for the 2 used in the enable circuit. What we're doing is simply shifting each bit of B left by 1 place and taking the most significant bit back to the other end. Although this computer contains just this one shift operation, to achieve the effect of shifting by several places, a program can simply just repeat the shift instruction several times. For example, shifting to the left 7 times is the same as shifting to the right one position. This exemplifies a general philosophy underlying the design of this computer. One goal is to implement a set of instructions that is representative of typical computers and that's complete enough to allow any program to be coded fairly easily. But most computers contain a whole bunch of other stuff that's thrown in just to make the computer fast at the more common tasks. For example, most computers would contain a number of different shift instructions so that any desired shift could be achieved in one instruction rather than needing several instructions. Including just a few more shift operations would really add nothing very interesting to the computer, so I just didn't do it. A common class of circuits is called the decoder circuits. For example, let's take a look at a 3 to 8 decoder. You can also have a 2 to 4 decoder or a 4 to 16 decoder, but here we've got a 3 to 8 decoder. It has 3 inputs, which can be interpreted as a binary value between 0 and 7. It has 8 output lines, and exactly one of them will be driven high, as selected by the inputs. Here's a circuit implementing the 3 to 8 decoder. Each input drives one relay, and you can see that exactly one of the 8 outputs will be driven high, depending on the states of the relays. Our arithmetic logic unit is capable of computing several different functions, and we use a 3 to 8 decoder to select which function will be desired. The function codes, which are labeled F0, F1, and F2, will select one of the 7 possible functions that this ALU can compute. The 8th line is used when no function is desired. It's essentially a 0 function when the 8th combination is input to the 3 to 8 decoder. The ALU will be disabled and disconnected from the result bus. Now we're ready to look at the entire arithmetic logic unit, the ALU. The inputs are shown in the upper left. There are the 2 8-bit input values, B and C, and there's the 3-bit function code, which selects which function will be selected as the output value. The function code drives a 3 to 8 decoder, which in turn will drive one of 7 enable units. The 8-bit logic unit is producing the AND, OR, exclusive OR, NOT, and SHIFT outputs at all times in parallel. If the function code is 4, for example, then the 5th enable unit will be selected and the exclusive OR output will be gated onto the data bus. The ALU puts its result on something that we call the data bus, which is an 8-bit bus that runs throughout the computer and connects to all the registers. We also see the sign and the carry and the 0 outputs. These 3 bits are called the condition codes, and later these will end up getting loaded into a 3-bit register which is named the condition code register. For the 8-bit adder, we see the sum output, which is labeled add in this diagram, and we also see an output labeled INC, which stands for increment. The increment output is just 1 added to the B input, with the C input being completely ignored. Although I didn't describe exactly how the increment function is computed, it's fairly straightforward. Basically, we block the C input to the adder using an enable-like circuit, and then we feed a 1 into the carry input to the least significant bit. We can summarize this rather complex diagram with this simpler diagram. This shows the inputs to the ALU, the 2 8-bit values called B and C, and the 3-bit function code, and it shows the 8-bit result, which is gated onto the result bus. We also see the 3 condition code outputs. So now let's ask how we can store a value in a register. All computers contain a few registers in their CPUs, and each register is a little memory unit that can store bits over time. To simplify our diagrams, let's start with a single bit. This circuit clearly has a memory of sorts. If the line labeled A is ever driven high, the relay will switch on. At that point, a feedback loop will prevent the relay from ever turning off, at least until the power is turned off. If the power is turned off, it will effectively erase the register, returning it to 0. So we can call this a bit relay, and we can take 8 of them and build an 8-bit register out of them. Now let's connect this register to the data bus using an enable circuit. By driving the select line high, we can gate the value currently stored in the register onto the bus. The select line allows us to read the value of the register in the sense of putting it out onto the bus, where the other parts of the computer can pick it up if they want. But we still have the problem of loading the register with a new value. Now we've added a couple of NOT gates, or inverters, and let's see how this works. When the line labeled load is low, power is supplied to the register and it will retain its value. So what happens if the load line goes high? Well, first the output of the first inverter will go low, causing all the bits in the register to be reset to 0. Then the second inverter's output will go high, which will open up the enable circuit. This will allow the value on the bus, whatever it is, to flow into the register, and some of the bit relays will switch back on. Now let's look at what happens when the load line returns to low. The output of the first inverter will return to high, resupplying power to the bit relays and latching the value into the register. Then the output of the second inverter will go low, turning the enable circuit off and disconnecting the register from the bus. To simplify things, let's draw a box around the control circuitry, which controls the loading and the selecting of the register. This separates it from the bit relays which actually store the data. Simplifying even further in this diagram, we're showing the load and the select control lines going into the control circuitry, and we're showing the 8 bits of the register as little boxes that might contain either a 0 or a 1. This computer contains 8 general-purpose registers. All 8 of these 8-bit registers are connected to the data bus in the same way. Each register has its own load and select control circuitry. Each register has a name. One register is called X, and another register is called Y. There are also other registers, and their names are A and B and C and D and M1 and finally M2, as well as X and Y. In addition to the 8-bit data bus, there's also a 16-bit bus called the address bus. These are the two main buses in the computer, the data bus and the address bus. As in many computers, some registers can be combined into larger registers. In this computer, for example, the X and Y registers are each 8-bit registers, but in some instructions, they're treated as one 16-bit register. So when they're treated together as a 16-bit register, they're called the XY register. There is also control circuitry that allows the combined register pair to be loaded from or selected onto the 16-bit address bus. Now we're ready to look at the overall architecture of the computer. Let's start in small pieces. First, we have the 8 general-purpose registers, which are named A, B, C, D, M1, M2, X, and Y. Each register can be loaded from the data bus, and each register can be selected onto the data bus. The little two-way arrows between each register and the data bus indicate that data can be moved both ways, both loaded from the bus into the register and selected from the register and put out onto the bus. Thus, there are 8 load lines and 8 select lines to control this data movement, at least for what we've shown so far. So now let's add in the arithmetic logic unit. The ALU always takes its inputs from the registers named B and C, and its result is always gated back onto the data bus, where it can be loaded into one of the other registers. We've also included a 3-bit register called the condition code register over on the right. It's only loaded from the 0, carry, and sign outputs from the ALU. Next, let's add in the 16-bit address bus. The XY register pair can be either loaded or selected so the data can move in both directions to the address bus. The two registers named M1 and M2 can also form a 16-bit register, which is called M. The combined 16-bit register pair can only be loaded in parts from the data bus. It can't be loaded as a whole from the address bus. When we talk about the instructions, we'll see that different registers are used differently, and we'll see that there's no need for loading M all at once. Next, let's add in the instruction register and the program counter, the PC. The instruction register will contain the instruction currently being executed and will be loaded from the 8-bit bus. Each instruction is 8 bits in length. While it appears in this diagram that data in the instruction register can never be used, in fact, this register will drive the instruction sequencing circuitry. We'll discuss sequencing later on. This diagram only contains lines carrying data. It doesn't show the control lines at all. The program counter will only be accessed as a full 16-bit entity, and it's not connected to the data bus at all. Next comes the main memory. The memory takes a 16-bit address as one input. During a store operation, when a byte is moved from the CPU to the memory, it also takes an 8-bit value from the data bus and stores this in its memory. During a load operation, the data flows in the other direction, from the memory to the data bus, and from there it can flow into one of the registers. Next, let's look at the 16-bit increment circuit. This increment circuit is completely separate from the increment portion of the adder in the ALU. There is also an associated 16-bit register, which is called INC, the increment register. The increment unit takes its input from the address bus, whatever value is on the address bus, and it adds 1 to it. The incremented value is then fed straight into the INC register. So when the load line to the increment unit goes high, the INC register is loaded with 1 plus whatever is currently on the address bus. And when the increment select line goes high, the value in the INC register is fed back out onto the address bus. Finally, there's another register called J, which is used during jump instructions. It's loaded in 8-bit pieces from the data bus, but it's only used as a full 16-bit value and put onto the address bus. Here's a close-up photo of the main memory unit. The memory is implemented with a single chip, which can hold 32 kilobytes. I could have implemented the main memory using relays with circuitry like that for the registers, but it would have made the whole computer really large. Building it would have consumed a huge number of relays, as well as a huge amount of time, money, and patience. The circuitry would have been exceedingly repetitive. With 16 bits of address, the computer can actually handle up to 64 kilobytes, but 32 is more than enough. The chip outputs are not powerful enough to drive a relay, so I used an array of 8 power transistors to step up to the voltage and current required for the relays. The memory chip is a 5-volt part. The relays and the LEDs all run on 12 volts DC. The memory chip loses all its contents when the power is turned off. The only way to load memory is by flipping switches by hand, bit by bit. It's a little tedious to toggle in long programs, but it's not too bad. So now let's take a look at how an instruction executes. We'll walk through the execution of an instruction that uses the ALU, for example, the add instruction. The first step is to fetch the instruction from main memory. We'll start by driving the select control line to the program counter high, which allows the address of this instruction to flow onto the address bus. Then we drive the read line to memory high, which causes the memory to look at that address and fetch the byte at that address and put it onto the data bus. Then we drive the load line to the instruction register high, which loads it with that value. Now the instruction register contains the instruction that we're going to execute. Before we execute it, we need to increment the PC. So we select the PC, which puts its address onto the bus, and we drive the increment register's load line high. This loads the inc register with whatever was on the address bus plus 1. But we need to get this value back to the PC. So next we'll select the increment unit and load the PC. This transfers the incremented address from the inc register into the PC register. Now the PC has been incremented by 1 and we're ready to execute the instruction. The instruction decoding circuitry, which we haven't talked about yet, will now look at whatever is in the instruction register, and the control lines will be driven high and low in whatever ways are appropriate for the instruction being executed. The ALU is always getting its inputs from the B and C registers, although normally the no-op code is sent to the ALU, so the ALU doesn't put anything on the data bus. But we're going to assume this is an add instruction, so the instruction decoding circuitry will, at this point, send the code for the add operation to the 3 function code inputs of the ALU. The ALU will respond by computing the sum and gating it onto the bus. The condition code bits will also be computed. In the next step, the load line for one of the registers, let's assume it's the A register, will be driven high. Also, we'll drive the load line for the condition code register high, so it will get loaded with the bits that reflect the result of this addition. So what we've done is we've added registers B and C, putting the result in register A and setting the condition code register to reflect the result. During all this, control lines were going high and low over time. These lines need to remain high for a short interval of time before going low. So next we need to look at the clock, which regulates this timing. Take a look at this circuit, which contains a switch, a relay, and a capacitor. When the switch is closed, the relay will turn on and the output will go high. Also, the capacitor will charge up, and this happens pretty quickly. If you're not familiar with capacitors, they're a little like batteries. You can charge them up, and then they can be used to power something, like a relay, for a short time until they're exhausted. However, batteries store a lot more energy over much longer periods of time. So next, if we open up the switch, the relay will stay on because the capacitor will power it. The capacitor will discharge in about 1/4 of a second, and then the relay will turn off. So let's look at that again. The switch is closed, the relay turns on, and the capacitor charges. The switch is opened, and then there's a short delay, and finally the relay switches off. The key is that the capacitor introduced a short, well-defined delay. It's this delay that we will build our clock out of. Now take a look at this repetitive chain of relays and capacitors. Let's start by assuming that relays B and C are on, like this. We'll assume that B is on because it's powered by its capacitor, which is slowly discharging. C is on because there's a path from power to its coil. Also, C's capacitor is also getting charged up. At some point, B's capacitor will run out and B will switch off. This will cause D to switch on, because now there's a path from power to D's coil. C will remain on, but the path from power to C's coil was broken when B was switched off. So C will stay on because now it's powered by its capacitor. So now let's connect relay D back to relay A. When C's capacitor finally runs out and C switches off, then A will now switch on. So we've got a cycle, and this will just keep on going. Let's look at one more step. The clock circuit is rather complex, but we can understand it a little better by looking at a timing diagram. In this diagram, time flows from left to right. We're showing a line for each of the 4 relays in this circuit, and we can see when each relay goes on and when each relay goes off. We can also see that at each moment, 2 relays are on and 2 relays are off. Now, what we'd like to do is we'd like to have a nice clean clock pulse. So in particular, we'd like to take these relay values and compute a nice clean square wave like this. We can compute or derive this clock pulse, as it's called, as a simple function of the 4 relays. By utilizing the unused switches on the relays, we don't even need to add any more relays to compute the square clock pulse. Here you see the 4 clock relays with their capacitors above them, and over at the right you see the square wave clock pulse. Now let's look at a finite state machine. Recall that a finite state machine has a number of states, shown here with circles, and it has transitions between the states, shown by blue arrows. In this particular machine, there are no choices. We just go from one state to the next, around in a circle. The clock pulse, the square wave from the clock circuit, will drive this finite state machine. On each clock transition, either from low to high or from high to low, the machine will move from one state to the next. We can even add some output lines. The idea is that when the machine is in state 1, the corresponding output line is high. So, as we move from state to state, each output line goes high in turn. At any one time, only one output line is high. So we'll call these output lines the timing lines, and we'll label them T1 through T8. Here's a timing diagram showing how these timing lines rise and fall over time. Most of the instructions in this computer require 8 units of time to execute. So remember the add instruction that we walked through? That can be done in 8 steps, or 8 time units. To see how an ALU instruction, like the add instruction, can be performed in 8 steps, let's look at a timing diagram for the control lines. This shows exactly when the various control lines need to rise and fall. By the way, each control line can be operated by a switch on the computer's front panel. So you could stand in front of it and flip the switches according to this diagram, and the instruction would be executed. But when the machine is running and the clock is driving things, the control lines will rise and fall on their own. So let's go through this diagram in more detail. First, we'll need to get the instruction from memory, and this step is usually called the fetch step. We drive the select line for the PC high, and we drive the control line to the memory high to make it load a byte onto the data bus. We wait one time unit to make sure the operation has time to complete and the memory output is stable, and then we drive the load line to the instruction register high, loading it. Next, we need to increment the PC. This is done in 2 parts. First, we load the increment register. Since the PC is being selected onto the address bus at this time, the increment register will be loaded with that value, plus 1. Then, later, we select the increment register and load the PC. Note that the first part is overlapped with the fetch step, since the PC is already selected onto the address bus anyway, and loading the increment register can be done in parallel with loading the instruction register, since they both use different buses. The final step is usually called the execute step. In the case of an instruction that uses the ALU, we need to first send the 3-bit function code to the ALU. The ALU function code comes straight out of 3 bits in the instruction itself from 3 bits of the instruction register. Then, after giving it a 1-unit delay for the result to become stable, we can load the target register, in this case the A register, and the condition code register. Now we need to look in a little greater detail at how these control lines are generated. This is the process called instruction decoding and instruction sequencing. So we have as our inputs the outputs from the finite state machine and the current value of the instruction register. The values from the finite state machine tell us more or less what time it is. In the case of the fetch and increment portions, all we need to know is what time it is. If, for example, it's time T1, T2, or T3, then the select PC control line needs to be high. In the case of the execute portion of the instruction, we need to know what time it is and what instruction it is. In any case, to compute the control signals, we just need a bunch of combinational logic. Recall that combinational logic is just functional. There's no state. The outputs are just a simple logical function of the inputs, and past states don't matter. The other kind of logic is called sequential logic, which involves state and memory. We don't need to work through all this combinational circuitry, but it does consume quite a few relays. I guess I'll leave this as an exercise for you to design. The combinational logic also uses, as inputs, the current value in the condition code register, but I didn't show this since there wasn't quite enough room in this diagram. Now, so far we've been assuming that all instructions take 8 units of time, but this is not quite true. Some instructions take longer. For example, there's a 16-bit move instruction. Since it needs to use the address bus to transfer its data, it's got to wait until the increment portion of the instruction has completed. Here's its timing diagram. You can see it needs 10 time units. So the simple finite state machine with only 8 states was not the full picture. The actual finite state machine has 24 states. Most instructions use fewer states and execute faster, but some instructions require all 24 states and therefore take much longer to execute. We can view the finite state machine as a sequence of states, numbered from 1 to 24, with 4 additional transitions that take a shortcut back to state 1. So there are actually some feedback lines from the combinational logic in the instruction decoding back to the finite state machine. There's some logic in the instruction decoding that figures out how many states each instruction requires and sends signals back to the finite state machine, which cause it to take one of those shortcut transitions if the instruction doesn't need the full 24 time unit. Now let's take a look at the instructions in more detail. For each instruction, we're going to show its encoding into 8 binary bits. It's so-called machine code. The first instruction is a register-to-register move instruction. It moves 8 bits from any register, the source register, to any other register, the destination register. The source and the destination are each specified using 3 bits in the instruction. If the source and the destination happen to be the same register, then the effect will be to set the register to 0. The next instruction is the ALU instruction. A 3-bit field in the instruction provides the function code, specifying whether it's an add instruction, an increment instruction, or whatever. The result can be put into either the A or the D register as specified by 1 bit, which is labeled R in this diagram. The next instruction loads a constant value into either the A or B register as specified by a bit in the instruction. The value is given right in the instruction in a 5-bit field. This value is sign extended, which means the most significant bit is simply replicated to fill the remaining high-order bits. This sign extension will take these 5 bits and turn them into a value between -16 and +15. The last instruction shown here is an instruction to increment the XY register pair. The next instruction to look at is the load instruction. It uses the 16-bit value in the M register as an address. This address is sent to the memory, and the byte read out of the memory will be loaded into either the A, the B, the C, or the D register, as specified by a 2-bit field in the instruction. The next instruction is the store instruction. Like the load instruction, the address is contained in the M register. The data is moved from a register, either A, B, C, or D, to the main memory. The next instruction loads a 16-bit value into the M register. This is handy for getting the address into M before a load or store instruction. In this instruction, the opcode is 8 bits, like in the other instructions, but the instruction is also followed by 2 additional bytes which give the full 16-bit value. This instruction takes a full 24 time units because the PC's got to be incremented several times and we've got to go to memory 3 times, once to get the instruction, then once for the next byte, and then one more time for the final byte. The last instruction on this diagram is the halt instruction. There is one relay, which I haven't mentioned before, that'll get set when this instruction is executed. This relay will latch on and stay on until you flip a switch to cut its power and turn it off. This relay, when on, will disable the clock and will have the effect of freezing the machine. So the execution of the halt instruction will freeze the clock in its tracks and will stop instruction execution dead. The next instruction is the go-to instruction. This instruction is a lot like the instruction that loads the M register, except that it loads the PC register instead. The 8-bit instruction is followed by a 16-bit value that's the absolute address to jump to. The jump will occur when the PC is loaded with a new value. The next instruction to be fetched will then come from this new address, which is the way go-to instructions usually work. The first part of the instruction execution does the fetch and the increment. Then, if it's a go-to instruction, the PC is overwritten with a completely new value. Then, the next instruction's fetch will use this modified value. One thing to note about our go-to instruction is that the PC is needed throughout the execution of this instruction. We can't load the PC until the very end. We need to increment the PC, then fetch the next byte, then increment it again, and then fetch that last byte. So, consequently, we can't load the PC until after we've finished fetching the entire 16-bit value. And this is the reason that we have the J register. The J register is where we put this value as we fetch it from memory. Only at the end do we transfer the bits from the J register to the program counter. The next instruction is the call instruction. It's very similar to the go-to instruction. Like the go-to instruction, the call instruction fetches a 16-bit value and ultimately moves it into the PC register, causing a branch in the flow of control. Like the go-to, it moves it first into the J register and then it puts it into the program counter. But before that final move, we also save the value of the PC in the XY register. This value of the PC is the value after all that incrementing, so it points to the first byte right after the last byte of the instruction. This is exactly the place we want to return to after the subroutine is finished. This is the return address, and as part of any call instruction, the return address needs to be saved. In this computer, the return address is saved in a register, the XY register, not on a stack. This computer doesn't support a hardware stack like most computers do. Most computers have a register dedicated to pointing to a stack, and there are instructions that push and pop things off of the stack. Usually, a call instruction will push the program counter onto the stack, which means storing it to memory and incrementing or decrementing some register. A stack in memory is a good idea because it facilitates recursive functions, and it doesn't consume a register to hold a return address all the time. However, this computer saves the return address in a register, the XY register, and not in memory. Of course, you could easily program a stack It would take several instructions, but you could do it. And you'd have to if you wanted to implement a recursive routine. You could dedicate a register to holding the stack pointer, but since register storage is so limited in this computer, you'd probably want to put the stack pointer in memory too. In any case, if all you want is a quick little subroutine that doesn't call other routines, the call and return instructions in this computer will work quite nicely. I should note that there seems to be a trend of going back to the idea of saving the return address in a register. The Spark architecture, for example, does it. The benefit is that subroutine calls and returns can be faster if you don't have to go to main memory at all. And most routines are not recursive, and many don't even call any other routines, so this is a very real gain. Anyway, we also need the return statement, and that's shown next. All it does is move the saved value from XY back into the PC register. This instruction can also be used to implement arbitrary jumps, indirect jumps, where the address is computed and stored in a register. This would be useful for implementing, say, the switch statement in some high-level language, or for invoking closures or something like that. The return instruction is actually a special case of a more general 16-bit move instruction, which is shown at the very bottom. The destination register can be either the PC or the XY register, and the source can be either the M, the XY, or the J register. If the destination is the PC and the source is the XY, then you just have the return instruction. Next, we have some conditional branching instructions, and these are shown here. They are all very similar, and they're very similar to the straight goto instruction. They each load the J register with the 16-bit value that follows the instruction byte. Then, in the last step, they move that value into the PC, but they do that conditionally. If the value is moved, the jump occurs. If the value is not moved, then the branch is not taken. There are several different tests possible. The first will do the branch, that is, the PC will be loaded, if the sign bit in the condition code register is 1. In other words, if the result of the last ALU instruction was negative, so the sign bit was set, then this instruction will take the branch. The second instruction will branch if there was a carry out of the most significant bit in an add instruction. The last two branch instructions test whether the 0 bit is set. In other words, they test whether the result was all 0 bits. The first branches if it was 0, the last one branches if it was anything else. You can use these last two conditional branches with an exclusive OR instruction to test whether two values are equal. If you exclusive OR two values together, then you'll get 0 if and only if they were the same value. Then you can use a test, and you could branch if the result is 0, which means they were equal. So finally, we can show a complete program. This is probably a little hard to read, so let me walk you through it. On the far left, we see the memory addresses. I'm only showing 8 bits of the address, not the full 16 bits, since there's not room and the program is so short anyway that all the upper bits are 0. Then you see the instructions. First, you see the instruction in binary. These are the binary machine instructions. They're not very easy to read, and they're even harder for the poor programmer to get right in the first place. But if you were to go back, you could check all these bits against what I just finished saying about the instruction formats, and there would be exact agreement. These are the bits that you would switch into memory before executing the program. The next column gives an assembly code version of each instruction. I haven't written an automated assembler for this machine. There's not really any need to, although some other people have. All my programs have been hand assembled. I guess I find this more to my liking. The last column gives another higher level version of this code. These are roughly equivalent to the comments that you would see, or at least that you ought to see, in any assembly language program. If you look at these comments, you could see what this program is actually doing. So let's take a look and see if we can figure out what this program is doing. Well, first we see a loop. Each execution of that loop increments the D register and tests to see if it's 0. Since D is first loaded with -7, the loop body is going to execute 7 times, and then the program will halt. So what happens in the loop? Well, we see Y getting shifted 1 bit on each iteration and tested. Then, if the bit is 1, it does something. So basically, we're looking through Y, and every time we find a 1 bit, we do something. And what do? Well, we add C to X. Also, we can see that on each loop iteration, we're shifting X 1 bit as well. So apparently, some sort of answer is being computed into X. The stuff before the loop does the same thing, testing the first bit in Y and initializing X either to 0 or C, depending. So maybe you recognize this pattern, maybe not. What we're doing here is binary multiplication. We're multiplying two 8-bit numbers. One number is Y. We're looking through Y, and every time we see a 1, we're adding C to the answer. Normally in multiplication, we would shift C 1 bit position to the left, then possibly add it to the result, then shift it again 1 more bit to the left, then possibly add it again, and so on. We're doing something similar here, constantly shifting the answer instead of shifting C. But this has the same effect because the shift is a circular shift. So I told you earlier that this computer has all the simple, important, basic instructions like add, but that some of the more complex instructions were left out. The idea is that you could always write a program to do the more complex stuff, and this is an example. There is no multiply instruction, but this program shows that you can certainly write a program to perform multiplication. This makes two important points. First is that this computer, like all other computers, has full Turing power. In other words, this computer can, in theory, do anything that any other computer can do. It can do anything that a Turing machine can do. All computers, in theory, have the same power and can compute the same class of functions. It's a Turing machine in exactly the same sense that every computer is a Turing machine. The second point is that the phrase, in theory, is very, very important. This computer can do an addition in well under a second, but it takes minutes to execute this program to perform even a simple multiplication. Adding a multiply instruction to the computer would obviously make a huge difference to any program that needed to multiply two numbers. So the point is that the instruction set design really, really matters. Computers with carefully thought out architectures will outperform poorly designed machines even with reasonable differences in clock speed and in implementation technology. I've gone out of my way to create a computer that's really simple and uses only 415 relays. I wanted something that would show the main core ideas inside every modern CPU out there today, but that wasn't too complicated. I hope that in this video I've been able to explain how a computer works in a way that's complete and comprehensible. If you'd like to go further with these ideas, there's an accompanying paper on the website that goes into the design in greater detail. And perhaps you'd like to build your own computer. I can't encourage you enough. This has been a fabulously rewarding project for me, and I've learned a great deal in doing it. So I would say go ahead, design your own machine, and build it. I'm sure that regardless of what you end up designing and building next, you'll have fun and you'll learn a lot from the experience, like I did from my Relay computer. I hope this video tutorial has been informative, and I welcome any feedback. I'm Harry Porter, and thanks for watching.